This video is going to take some time to walk through and prove the ratio test, right? And so let's first remember what the ratio test says from our calculus days, right? So our ratio test, it says, suppose that S sub n is a sequence of positive terms, right? So every single choice of S sub n is bigger than 0. And that the sequence of the ratios, right? So we're going to take the next term in the sequence S sub n and divide it by the previous term. And let's say that that converges to L. If that value of L is less than 1, then this sequence, original sequence up here, has to actually converge to 0. So let's go through and let's take the time to prove that. So our previous corollary, so 4.2.5 that we looked at real briefly right at the end of the last theorem, right? It said as long as we have positive terms, a sequence of positive terms, then our terms that are all greater than or equal to 0, then if it converges, what it converges to is also greater than or equal to 0. Right? So we have a sequence of positive terms, so all of our terms are greater than or equal to 0, and so that has to be convergent to something that is greater than or equal to 0. Right? So our corollary, it implies that value of L has to be greater than or equal to 0, right? So up here we have terms that are all going to be non-negative. They're all going to be actually positive terms, right? So now let's suppose that the value of L is actually less than 1, right? So it's greater than or equal to 0, but it's less than 1. Right? This is part of our hypothesis right here. If L is less than 1, that it's going to force the limit of S sub n to be 0. That sequence is going to have to converge to 0. So suppose L is less than 1. If L is less than 1, then there exists C and the real numbers such that 0 is less than or equal to L is less than C is less than 1, right? So there's a real number between L and 1. Let's let epsilon be equal to this value of C minus L, the difference between C and the value that we think it's converging to. So again, make that observation that that value of epsilon is bigger than 0. This is a valid choice for epsilon. Sometimes we could get into the habit of choosing an epsilon that when we're working with just variables, we can go through and prove things, but overlook the fact that we've chosen a negative value of epsilon, and so it's not actually a legitimate value of epsilon, right? So that's why we make those observations. Then, since S sub n plus 1 over S sub n converges to L, we know that there exists a natural number n such that n greater than or equal to n implies that the distance between S sub n plus 1 and S sub n over S sub n and L, that is less than epsilon. So let's let k be equal to n plus 1. Then if k is equal to n plus 1, then for all n greater than or equal to k, we have n minus 1 is greater than or equal to n. So that s sub n over s sub n plus 1 is less than L plus epsilon. Which is equal to L plus our value of epsilon was C minus L, which is C. All right, so S sub n over S sub n plus 1 is less than that value of C. It follows that for all n greater than or equal to k, 0 is less than S sub n is less than S sub n minus 1 times C is less than S sub n minus 2 times C squared is less than S sub n S sub k times C to the n minus k. All right. Let m equal S sub k over C raised to the k. And we get zero is less than S sub n is less than m C to the n for all n greater than or equal to k. Since we have 0 is less than C is less than 1, that value of C is between 0 and 1, we have C to the n is going to converge to 0. Right. Thus, the limit n goes to infinity of S sub n that is converging to 0. And we are done. All right.